Today we have finding elements of the trajectory of the material point. This article 8.6 of the book Mechanical Systems Calculations of the Marine Facilities. We have the exercise assigned kind of the parametric assignment, the coordinate form of the motion of the material point. So we have assigned two coordinates. We will do the exercise in the Mathcad computer algebra system. So yeah, just this fragment of the Mathcad page, screenshot of the Mathcad page. So we have two formulas of the coordinates variation. There's one formula is the pattern of the change of the abscissa of the material point motion is 6 by multiplied by cosine in the brackets pi by t divided by 6 minus 2. Yeah, and the ordinate parametric assignment in the components, in the coordinate components of the material point, ordinate is assigned mean the not the sign of the equality, but the sign of the assignment as we can shift columns together, press to just can select this operation from the panel of the Mathcad, but if not the panel Mathcad, we just have to press together shift columns. Or ordinate pattern independence on time is 3 by multiplied by cosine in the brackets. The argument of the cosine is pi by t divided by 3 plus 4. And as well, we can find the for the initial time to find the coordinates of the point and find the point velocity, the components of the velocity to find the acceleration of the point and find the components of the acceleration of the point in the coordinate system, and as well in the moving coordinate system associated with the point. That is the natural assignment. So so let me repeat, it is assigned to find the coordinates of the material point. Next is assigned to find the velocity of the material point, magnitude of the velocity, and to find the accelerations of the components of velocity and the magnitude in the coordinate form. And next find the acceleration of the material point and the components of the acceleration in the coordinate form and in the coordinate system associated with the moving point. Okay, so we have assigned the time is equal to t to this all indexes, I mean velocity of the point, and the acceleration we have find a time t1 assigned 2 seconds. We can immediately find it as the coordinates of the abscissa and the ordinate in the Mathcad. Just the equality of 2. This is a function assignment. The variable is t here. By the assign shift column, just the equality, the sign of the equality, what is equal the ordinate and abscissa. Okay, we first have to find the coordinate, perhaps to find the shape of the trajectory. Perhaps we have to exclude the parameter of time. Then we have the trajectory. To do that, to include the parameter of time, we can use the known formulas from the trigonometry and the cosine to alpha, perhaps to alpha. This is pi by t divided by 3, pi by t divided by 6. This is two angles of the ordinate of the abscissa. And this one formula we have to use, considering that. And then we can, from the first equation, define the cosine as the x divided by 6 plus 2. Yeah, from the just for simple mathematical transformation. After that, having the cosine of pi by t divided by 6 as x plus z divided by 6. We can next find when substitute this cosine into the second formula after they have this transform of the cosine to alpha. This is cosine of 2 alpha, two angles of this one angle. The angle, I mean, argument of the trigonometric function. Then we will have the dependence of the ordinate on the abscissa. So this is understandable with exclusion of time. The trigonometric dependence on time. 1.6 squared here came from this one formula. Yeah. So when we substitute this cosine p to 6 this instead of here instead of the cosine, which is equal due to the first formula into the second one. So next we can do in the Mathcad. This is a screenshot from the Mathcad computer algebra system. This is specified set of the magnitudes of the variable abscissa. This is the formula got previously here. Here we have the formula. We have here specified in the Mathcad. Next we have the vector of the magnitudes of the, if the x we define as the vector, this is a vector shape, this is just a matrix column. Then we have the result of the formula used as a vector as well. And we can look at this definite one, the shape of this dependence here. And we have that the dependence is parabolic shape. Here is of the parabolic shape. Yes, this is understandable. Next, what we can say about the velocities. The velocities first in the Mathcad, we just have to remember that the velocity is the derivative of the coordinate. Component of the velocity projection on the abscissa axis, derivative of the coordinate dependence on time. So we in the Mathcad use in the option in the panel of finding of the derivative, that is the velocity on t dependence equal shift columns equal, not equal, but assign the derivative of the x derivative. Next we can find in the assigned time t2 equal to 2 the magnitude of the component of the velocity on time is equal to 2, at time t equal to 2, equal to minus 2.721. Okay. The same we can find the component of the velocity projection on the ordinate axis. On the ordinate axis we can find that the velocity, yeah, it is just assignment from the panel of the math of the Mathcad. Next, we can, using the operations available in the panel of the Mathcad. Next, we can find that ordinate of the velocity minus, etc. So, having two components, we assign that v1x is not a definition of the just only shift and underline like that. We can find just the magnitude with the index, not the component of vector. But we assign that this magnitude v1x equal to the velocity on 2, yeah, velocity on 2. We redefine this, define new one magnitude. We define another one magnitude, velocity of on 2 times t equal to. Next, we can find the the magnitude of the velocity by the Pythagorean theorem as a square root of total of two squares of the components of the orthogonal perpendicular components of the velocity. We can find that the velocity magnitude of 3.848. Acceleration of the point, we can have to find the acceleration as well. We can find the second derivative. So the assigned trajectory of the motion of the material point, but it could be the first derivative of the velocity. So we can find the velocity as variable. The velocity assigned here, we can find derivative by use of the Mathcad math operations panel, and we can find the velocity. This is assignment shift column operation one, columns and the equality. Next is just to make a check what is the component. We would not be, this is not mandatory to do the check of the acceleration component because we have assigned only the magnitude of the, but anyway we did. So this is a component of the acceleration in the projection on the ordinate axis. The second derivative of the component of the velocity in projection on the ordinate axis here got a little bit before. So this is just check what is the component in the magnitude 1.645. Next, we redefine the two definite values, a1x and a1y, n1y, as they previously got the magnitudes of the second derivative of the coordinate assigned or the motion of the material point. This is the first derivative is vx and the second is ux, ax, or sorry, this a y, second derivative of the y of on t, but this is first derivative of vy on t. Yeah. After that, we can find the same the sequences finding the velocity. We can find that the acceleration magnitude is square root of the total of two summands each component power to square degree A1 equal to 1.839. Okay, so next we have to find the radius of the curvature. The radius of the curvature can find having the formula rho for the definite time exactly. We have assigned time 2 seconds. Yes. So we have the normal acceleration as the square root, but the same by the use of the Pythagorean theorem. Square root of the difference of the squared. This is a diagonal of the result. This is a component tangential, so here to have the tangential component. Yes, in the squared power. The finding of the tangential component of the acceleration. How to do that? This is the ratio. In the numerator we have total equal to the scalar product of the acceleration by the velocity. The scalar product equal to the total of the products of each component on the between each other. So we multiply the component A1x by the component of the Vxt. Yeah, 1x is equal to the assigned time period. The second for the projections of the acceleration and the velocity onto the ordinate axis. So this is scalar project here. And we divide by the magnitude of the velocity, and we can find the magnitude of the tangential acceleration. And so a normal acceleration perpendicular to the tangential one by the Pythagorean theorem. From the hypotenuse, we subtract the magnitude of one leg tangential, another one leg normal. So we have to apply the power to second degree square root as a characteristic for the Pythagorean theorem. So this we can do in the Mathcad. Tangential acceleration. This is a scalar product of the acceleration by the velocity divided by the velocity magnitude. We can find the tangential acceleration. Next, we can find normal acceleration as by use of the Pythagorean theorem, normal acceleration. So we can find the radius of the curvature of the in the assigned point. The radius is the squared velocity magnitude divided by the normal acceleration. So we can find that, but the radius of the curvature equal to 8.485. Yes. So, and we can show this all onto the scheme of the point located on the parabolic trajectory. And we have the velocity, the components of the velocity. We have the components in the coordinate system, components of the acceleration, projection on the abscissa axis, projection on ordinate axis. Next, we have the total of the, we got previously the projections of the acceleration. So, okay. This one, negative magnitude of the projection, this is positive. So we can have here the negative magnitude of the projection, this positive one. Okay. This is a total, and this is in the moving coordinate system associated with the point. The moving coordinate system possesses the normal acceleration and the tangential acceleration. The if tangential acceleration contradicts the velocity, that is the slow in motion. In the definite one time moment as 2 seconds, this is slow in motion with the tangential acceleration negative. Okay. So we have another one exercise, exercise 2. The coordinate form, the pattern, the point motion of the plane is parametrically specified as we have sine and cosine of the same argument, the same assignment, but in the parametric form of the coordinates. 5 multiplied sine in the brackets, we have pi by t divided by 3, and y ordinate equal to 3 plus 5 by cosine p multiplied by t divided by 3. This form of this patterns of the motion of the components change of the moved material point looks very like that is that circle, as we get a little bit later. To find this shape of this trajectory, we have to exclude the time parameter from these equations, from metric equations, and redefine y by x, and this we use the known dependencies as sine and cosine squared total together equal to 1, and that from the first equation, we derive the sine factor equal to x divided by 5, and from the second we derive the cosine factor, y minus 3 divided by 5 equal to the cosine. Yeah, and then when we raise to the second power the each sides, the left and the right side of this equation, and squared power to the square degree, we have to equate to 1. This is the known dependence from the trigonometry. Total of the squared sine cosine equal to 1. So, and this we can see that this is the circle with the radius equal to 5, and the second coordinate y is here. The center of the circle is 0 by the abscissa, and by the ordinate we have minus 3 here, minus this. We have plus 3, yeah, plus 3 because we subtract minus 3 in the numerator, says here squared. So this is definition of the trajectory on as a circle shown on the figure H, point 6 point H. We center at the point with coordinates 0 and 3. Keep working. Next, the intersection points with the coordinate axis of circle trajectory of the point M are, if x we have 0, then the intersections are y. We substitute on the formula got here the 0 instead of x. We can find what is the y. Y is equal to 3 plus minus 5. And if y is 0, the intersection is the ordinate axis, so we have the same substitute in the formula 0y for the circle. Then we have that x will be equal to plus minus 4 meters. The initial position of the point of the trajectory is determined by the coordinates at t equal to 0. We can substitute on this equation, and we can find that the initial location of the point is this is the location of the point we considered at the 0 point when the time is 0. Here, etc. We can find that 0 and 8 meters. Oh, excuse me. Another 1.0 and 8 meters. Yeah, yeah, this could be initial 0 and 8 meters. M0. Yeah, M0 here located. Yeah, and the position of the point M1 on the trajectory 1 second after the motion, we can substitute 1 and can find by the originally assigned parametric dependencies. We can find location of the time equal to 1, the projections of velocity of the point onto the plane x. So we have to find the derivatives from the originally assigned parametric dependencies, derivatives from these dependencies, and next we can find it, which is the shape of the function of the velocity. This is a shape of the function meters per second in the coordinate system 0xy. And 1 second after the motion, the start velocity, we can find the projections if we assign t equal to 1, we substitute 1, etc. We can find these velocities. We can show this in the point after 1 second. This is a point m1 equal this components of velocity v1x, v1y, and by the tangent to the trajectory, we have the resulting magnitude of the velocity square root of 2 squares of the v1x squared plus v1y squared. Square root is 5.24 meters. And the projections of the acceleration, the second derivative of the originally coordinate shape of the assignment of the motion, or the first derivative of the velocity got previously. This is dependencies from the velocity got here. This is velocities, and the accelerations components on the axis projections is equal to this got by the differentiation of the velocity. Dependence 1 second after the start of the motion, we can substitute t equal to 1, and we can find what is the components of the acceleration minus 4.75. This is components of the acceleration minus 4, etc. This is component of the acceleration on the ordinate axis is minus 2.74. The magnitude of acceleration can find square root by total of 2 squares of the components by the Pythagorean theorem 5.84. The projection of acceleration onto the velocity. To do that, we have to the acceleration. Yeah, excuse me. This is projection of the acceleration, the velocity, the derivative of the velocity by time. How to do that? First, we have to find the scalar product of the acceleration, components of acceleration on the velocity, components of the velocity. We have a numerator divided by the magnitude of the velocity. After the substitute, we have that the tangential acceleration is almost zero. That means that the motion of the point by the circle trajectory is almost with not the tangential acceleration, with a constant velocity. The normal acceleration next we can find is by the square root of the difference of the the acceleration got previously. So it's acceleration magnitude squared 5.48 minus a squared tangential is this almost zero acceleration. This is due to the Pythagorean theorem. Then to the time t equal to 1 second, we have that the normal acceleration almost equal to the total acceleration, because we have no tangential acceleration. It's equal 5.48 meter per second. And the radius of trajectory curvature 1 second after start of the motion is v squared divided by the normal acceleration. Normal is 5.48. The velocity we got previously is 5.24 is squared. The equal the radius is 5.01, almost 5 meters. The radius of the tangential acceleration of the point me is zero. Since velocity of the point does not depend on the time and is constant in the magnitude, that is tangential equal to zero. Yeah, we can this do with a substitute of the original parametric dependence. This is the equation. Questions and comments. H61 specifying the Mathcad computer algebra system the trajectory of the point on the plane in parametric form, finding the area for determining the coordinates of trajectory along the abscissa ordinate axis. Mathematical transformation of a given law of the motion into the coordinate form with the exception of the time parameter. This is just explaining what we have to do to find the trajectory shape in the Mathcad or with not the Mathcad. We have to exclude the time parameter. If we to find the trajectory, we have to have the dependence of the ordinate on abscissa. Okay. H62, determining the coordinates of the trajectory of the point in the Mathcad in the form of vector arrays. The symmetrical values along the abscissa axis within the definition area and the graphical plotting the trajectory. In the Mathcad, they have the option to have the graphic plotting on the trajectory when we assign to plot the graph. So we have the windows in the panel of the Mathcad where we have to in the Mathcad sheet we have the windows to specify the arguments and the function to have the graphic plotting of the trajectory. Yeah, we can do that in the form of the vector arrays, finding of the point trajectory points as well. If we specify the argument is the abscissa, finding the trajectory as we specify the vector of the abscissa argument, then we will have the vector of the ordinata. If we have, besides of the specification of the range of the variation of the abscissa, we will have the formula for finding of the ordinata. The ordinata will be as the vector array, the column, matrix column. H63 determination numerical taking by numerical taking derivatives of the Mathcad computer algebra system, projections of the velocity and acceleration of a moving point onto the coordinate axis and the values of the velocity and acceleration from their projections. To find the values of velocity and acceleration here in the projections, we can use the Pythagorean theorem, a square root of the total of two components squared. And in the Mathcad computer algebra system, we have the possibility to find the derivatives, not having the derivatives in the analytic approach, just only by the digital use of the Mathcad computer algebra system. In the panel of the Mathcad, we have the operations, mathematical operations, and in there we have the access to find the derivatives. It is finding the derivatives or finding the a particular derivative for functions of the many variables. So we have we used the operation of the Mathcad to find the derivative. As well, we can find in the Mathcad the derivative as not the magnitude for definite time moment, but we can find the derivative as the function. The Mathcad gives a possibility to, if we assign the function, then derivative, it can indicate in the worksheet as the function. Finding the analytical definition of derivative is possible in the Mathcad. H64. Using velocity projections found in the Mathcad when specifying the point's motion parametrically to determine the sines and cosines of direction angles of the point's trajectory line. To find the projection of for example, of the acceleration on the velocity direction. So we can first, instead of finding the cosine, the angle of the cosine between the acceleration and the velocity acceleration in velocity direction, instead of finding the cosine or the inclining, to find the projection of the acceleration on the direction of the velocity, that is to find the tangential acceleration. We can use the approach to find the scalar product of the acceleration velocity, having acceleration and velocity got or specified in the coordinate form, And actually, we have to divide this product of the acceleration on the velocity. We have divided this product, scalar product, to the magnitude of the velocity. We will have the magnitude of the tangential acceleration. Next, we can find the normal acceleration. If we have total acceleration, then normal is the acceleration of the point is by the Pythagorean theorem, square root of the difference squared, the squared acceleration minus the squared tangential component of the acceleration. So we thus can use the scalar product of the velocity and acceleration to find the tangential acceleration. H65, determination of the projection acceleration into the direction of the motion of point, the tangential acceleration, and projections onto normal perpendicular to the direction of the motion of the point E, the projection acceleration is the a natural way of specifying motion when the origin coordinates is associated with the point. The tangent axis coincides with the direction of the motion. The normal axis is directed along the radius of the curvature, and the binomial axis is the vector product. This is definition of the natural way of assigning of the motion of the material point if the reference coordinate associated with the point and the three axes we have in the space. On the flat we have only two axes, and the first axis is the tangential axis, another one is a normal axis, and next one is a binormal axis. This is three axes generally for definition in the coordinate system of the velocity and acceleration of the point when the coordinate system moves together with the point with a definite with definite adoption the direction of the axis with the direction of the point motion. So, and to determine projectile acceleration to the direction of the motion of the point, we, as I told a little bit before, we can use to find the tangential acceleration first projection of the acceleration onto the tangential axis. We can have the product, the scalar product of the acceleration assigned in the coordinate form onto the velocity assigned in the coordinate forms for the fixed coordinate system. And next, to divide this all to the magnitude of the velocity, we will have the tangential acceleration in the moving coordinate system. And besides, by the Pythagorean theorem, we can find the normal acceleration and projection of the acceleration on the perpendicular direction by the normal axis in the right coordinate system moving with, by is this natural way of assigning of the motion of the point having in the moving coordinate system. 866, the analytical determination in the parametric form of specifying the motion of projections of point, velocity, and acceleration by taking derivatives of the trajectory, as well finding a final values of velocity and acceleration. we as well can find the projections of the velocity and acceleration in analytic form. In the Mathcad, this is option available in the Mathcad. In the math operations, we have the option of indicated in the math operation in the Mathcad by the right arrow. By the right arrow, we can, instead of equality, if we predefine shift columns first, we predefine the index of the components of the acceleration or the velocity. If we have this predefined in the Mathcad, so in the next we can find the analytical dependence. If we specify as well before the parametric dependencies of the coordinates on the time moment, so we can find the derivative by time, for example, of the components. This will be velocity, and the second derivative is acceleration. And we have the analytic dependencies, not the data, but analytic. If we do not define by the sign of the equality, but if we will use the sign of right arrow from the panel of the Mathcad, math operations panel. H67, the determining of acceleration projections on the tangent axis to the tangent trajectory on the normal axis when the natural method of specifying the motion of the point is used with the velocity projections found by the specifying the motion parametrically. Yeah, having the velocity, having the coordinates specified parametrically, we can find the components of velocity specified parametrically as the derivatives of the coordinate by time of a specified parametrically. Next, we can find the components of the acceleration specified parametrically, as well as the second derivatives of the assigned dependencies for the coordinates, or the first derivatives of the got dependencies of the velocity. And having that together, we can find the tangential acceleration by the use of the approach of the scalar product of the acceleration by the velocity. This is the total of the component, one component of acceleration multiplied of this one component of velocity plus second component of acceleration multiplied by second component of velocity divided by the magnitude of the velocity. This will be the component of the acceleration on the axis associated with the direction of the motion of the point. And if next we will use the Pythagorean theorem, we can find the perpendicular acceleration that is normal. We had the magnitude of the acceleration, then the normal is square root of the squared magnitude of the acceleration total minus squared tangential acceleration got previously by the scalar product of the acceleration by the velocity. H68 determined radius of curvature of the point trajectory by found the velocity and by the magnitude of the acceleration projection onto normal axis. If we have normal acceleration and if we have the velocity, the radius of the curvature of the trajectory equals to the ratio of the squared velocity to the normal acceleration magnitude. So this is what we can find, how we can find the radius of the curvature of the trajectory. And this perhaps all questions. Yeah, this is all. And let me show the file of the Mathcad used for this one presentation. The file of the Mathcad. Okay. This is a file of the Mathcad we use here. So first we have the parametric dependencies of the incardinal form of the motion of the material. This is the first exercise considered in the specified presentation. The abscissa by the cosine pi, the ordinata, we remember that we used the dependence of the double angle in the argument of the trigonometric functions. I mean, after the substitute, after definition of the cosine and sine of the angle by the double angle, the formula from the trigonometric we had today in the presentation. Anybody can check what is the formula or dependency cosine double angle by the square cosine. Next, we can define this we can derive the ourselves with not a Mathcad, the cosine from both sides. We can substitute if we after transformation to the second one angle to the this one argument, yes, and that substitute derived from this equation of the cosine into the second one, we can find this analytical dependence, and we specify x, the variable, this one variable, as the definite array, and the formula of this one is with not the time parameter. This dependence for the definition of the trajectory definition of ordinata by abscissa with not the time parameter, and we exclude time parameter by this way, and after that, when we redefine, we watch please at the Mathcad. After the first definition, shift columns is definition, shift columns, it's not equality sign. T assigned as 2 seconds. And this is not equality. And after the second definition, the Mathcad adopt the last one for the next calculations. For the first one is neglected for the next after the second assigning of the same indexes as x we assign second one and the y we assign this. And we use the Mathcad opportunities to have the trajectory graph as abscissa ordinata here, y over x, etc. This is a race we are specified from -4 to 4, and the same the y we have as the array. And this is a definition of the accelerations we have. Just rate frames here. What was it? Because to do these transformations, we have to be assigned. We have to have the assigned in the parametric shape dependence on t as we had originally had. But next we assign in the analytic dependence excluding with exclude of the time moment. So we have to exclude these active two operators to use the next one. This, let me remind again, as we select these two operators, we click the right part of the mouse and we do the exclude, these operations exclude. Yeah, we have exclude, no more graph we have, but we have now the action of the previously decided the assigned parametric dependencies. So for this parametric dependency on time, we have determination of the components of the velocity as a derivative got from the available, this is math operations. It's this derivative from the math operation, the panel of the Mathcad. And we have the same for the derivative by time of the second one, or parametric dependence here, second parametric dependence y on t, excluding the analytical dependence from the Mathcad sheet. In these dependencies, we had to have the graph of the trajectory to show the shape of the trajectory. But we no longer need to find the components of the acceleration and the velocity, so we exclude from the Mathcad page active these two formulas, and we have first assigned active again. So we find the components of the velocity by derivatives finding with the operation the Mathcad. We do not have to do the find of the derivatives by ourselves. So the Mathcad can do that, and next after that we can find the components of this velocity for the time assigned equal to 2, and by the Pythagorean theorem we redefine the variable in the Pythagorean theorem, the magnitudes in the Pythagorean theorem under the root of total 2 squares. We can find the total velocity, and the Mathcad computer algebra system allows as well to find the analytical decision, not to find the magnitudes of the components for the assigned time moment, but to find what is the analytical dependence for the corresponded for the assigned formulas, what analytical dependence. How to do that? We just the assignment. The assignment, this is the definition of the analytical dependence. But to see that, to see, not to assign, to see this assignment for this formula, what is analytical dependence? This analytical dependence. To see this analytical dependence, we have to use in the math panel the operation, the right arrow. Right arrow shows us the analytical dependence. This is available in the Mathcad. The same for the acceleration we do, and after that we can find the tangential acceleration as the scalar product of the acceleration velocity having components of the velocity and components of the acceleration here. And by the magnitude of the velocity, we have the magnitude of the velocity by Pythagorean theorem got here, and we have tangential acceleration. Next, we have we assigned as the normal acceleration is the square root of the acceleration got magnitude acceleration of 1.839 squared minus the tangential acceleration. So we have normal acceleration by the square root of v. Next, we can find by the assignment of the v squared velocity by the normal acceleration as the radius of the curvature of the trajectory in the definite one point assigned point. We have assigned t1 equal to 2. And yeah, so thank you.